We're solving problem 20 from the 2020 AMC 12B. Two different cubes of the same size are to be painted, with the color of each face being chosen independently and at random to be either black or white. What is the probability that after they are painted, the cubes can be rotated to be identical in appearance? So, for this problem, we can denote them into a few different cases. This is primarily just case counting. Case 1, our first case. The black to white ratio, or white to black, is going to be equal to 0 to 6. Now, let's assume this is the black to white ratio. And if this was true, then the number of ways would just be 1 squared or 1. So this would be one way for this to happen. Now, you might be wondering, we're going to have to count the white to black ratio 0 to 6 too, right? And you're going to be correct, because it's going to be a different configuration such that they can be rotated to be identical in appearance. But for simplicity, let's just consider this as black to white ratio. And then in the end, when we're adding everything up, we want to multiply it by 2 to the ones where you need to multiply by 2. So then it would be easier for us to count, rather than to just add two eventual squares together. Case 2 now. The black to white ratio is going to be, now to proceed from this point, we can just start adding 1 to the blacks and removing 1 to the white. So just 1 to 5. We calculate this ratio. Well, this ratio, 6 choose 5, right? 6 sides of a cube and choose 5 of them to be white and 1 of them to be black. And then this is just going to be equal to 6. So the number of ways for this case is going to be 6 squared, or 36. Now, case 3. The black to white ratio is going to be equal to 2 to 4. So you see we're just adding 1 to the black and removing 1 from the white. Our ratio is then going to be 6 choose 4 of the squares to be white. But then in this case, well, we have 2 of the blacks. And the only ways for this to happen, if like there's 2 blacks, is if the 2 black squares are touching or they are opposite to each other. So what I mean is, if we have a cube here, the black squares could be configured such that they meet at this point. Or they can also be configured such that they don't meet at a point, but rather at 2 different sides. So like, imagine these dotted lines represent the other sides. This could be black, and the other opposite end could be black. Now, for this case, when we're doing 6 choose 4, we're counting the number of squares for this case, the touching ones. So if we count the number of ways to do this, we have to subtract the opposites from each other, the pairs of opposites. And in a cube, there's 3 pairs of opposite sides. So we subtract that. So, and this gets us to 12. But then we also have to add back the 3 and square that. So our total number of ways is 12 squared plus 3 squared ways. Now, we subtracted 3 here and added back a 3 squared here because we weren't considering the case where they were in fact opposites. That's another individual case. Case 4. Black to white ratio is equal to 3 to 3. And this is going to be our last case, because for all of these, we can just multiply it by 2. And for this one, well, the ratio stays the same even if it's white to black, because these are 2 equal numbers being like compared, right? Then there's also 2 ways for this to happen. One way is that, well, if you have 3, say, black squares or 3 white squares, let's just do black, 3 of them could be like all meeting at one vertex, like this one. So assume this is a random cube, and these are 3 sides, and those 3 visible sides are shaded. That's one. Another way that shaded cubes can have like 3 sides shaded is that if they're all in a sort of line. Now it's a 3-dimensional line, so it's gonna go from this one, the outer one, to the top one, to the other opposite one. It might be hard to see, but the configuration of a cube when you fold it out is gonna look something like this. I believe something like that, or is it? Yeah, but it's gonna look like a cross, and basically what we're trying to take out is that, like, if there's like a 3, right, and they're in a row, it could be this 3. It's just that it's 3-dimensional. So that's our 2 cases, the ones in a line and ones touching. Now, for the ones, say, touching, that's gonna be the one we're counting first. 6, choose 3, and then we're gonna subtract again 3. We're gonna have to subtract the number of other cases, or let's just count this one. We subtract 8 vertices because this can meet at 8 vertices. That gives us 12 again. And then there's 8 ways to do that one. And then this brings us to 12 squared plus 8 squared ways. Now, when adding this sum of ways up, you have to remember that we're not multiplying this by 2 because the ratio is always the same because it's 3 to 3. Then our fraction is going to be 2 times 1 squared plus 6 squared plus 12 squared plus 3 squared plus 12 squared plus 8 squared, all divided by 2 to the power of 12, which is the total number of ways this can happen. And once simplified, this fraction is going to give our answer of 147 over 1024. So that is our answer for this problem.